So this is a very interesting time with COVID-19 and the coronavirus, and webinars and remote meetings are really a great way for us to continue working and learning together. So I'm glad we have the opportunity to do this and to reach several of you, and I hope that all of you are healthy and well, as are your friends and family. So my name is Holly Campbell. I'm going to be the presenter for our webinar today. I'm a public service assistant with the University of Georgia Warnell School of Forestry and Natural Resources. And my colleague, Dr. Jason Gordon, is with me online right now. I have him muted, so Jason, if you want to speak up, just let me know. I'll keep an eye on the chat box. And Jason Gordon is an assistant professor of community forestry here, also at the Warnell School of Forestry and Natural Resources. So just briefly about myself while I'm waiting to see if Jason wants to add anything. So I primarily work in outreach, and that's also similar to cooperative extension, and my work focuses on community forestry and wildland fire. So I work in prescribed fire and wildfire education as well. But I have a background in soil science, and so Jason and I are sort of sharing the webinars that are within this series. I'll tell you a little bit more about the series in a second. And so that's why I'm covering this one. I also wanted to put out a special thanks for Dr. Larry Morris, who has provided some input on this presentation, and so I really appreciate his input. Okay, so as I mentioned, this webinar today is part of a series that Jason Gordon and I are providing throughout this year, and our goal is to increase knowledge in community trees and community forestry topics, specifically for Georgia Cooperative Extension Agents. So that's our target audience, but we open the webinars to anyone who would like to join and who has an interest in the subject areas. So in this webinar in particular, we're going to cover various aspects of soil management for community trees and why this is important not only to the health and longevity of trees in our communities, but also to the health of our ecosystem and planet. So when I refer to community trees, I'm talking about trees in urban, suburban, and rural communities and the soils that surround those trees. But let's look at a little bit of foundation here. Let's think about the world that we're living in and why soil management and care of our trees is so important. We live in a world that's ever growing as far as human population. And as you see in this figure here, in the 1950s, we're at about 751 million. Now, this is specifically in urban areas. This is not necessarily just the world population. So it's the world urban population. 1950s was about 751 million. We moved up just a couple of years ago to 4.2 billion, and it's projected by 2050 that we're going to be at 6.7 billion people in urban areas. So that's a 68% increase from where we are now. And we have over 50% of our population in the world lives in urban areas. Let's look at our own country here. So in the US, North America is one of the most urbanized areas in the world. And per the last census, of course, it's going to be updated now with the new census coming out, but we had just about 82% of our population lives in urban and suburban areas. So I know I've seen several of you are from out of state, but again, our target audience are Georgia Extension Agents. So I'm going to focus on the state of Georgia right now, which could be a similar situation in the state that you're in as far as growth goes. Georgia is one of the fastest growing states in the nation, and it's the fastest growing state in the southern region. In the last census, 2000 to 2010, the population in Georgia increased by over 18%, and this is 2 times the national average. And a lot of that growth is occurring around our metro areas, specifically Atlanta. We have some of the fastest growing counties around Atlanta. And the Atlanta metro area, now this covers sort of a large area outside. It's not just the city of Atlanta, but it covers a lot of the suburbs surrounding Atlanta, is one of the largest metro areas in the southern region with over 5 million people. And also our coastal and mountain areas are growing as well. So we're an ever growing and expanding state, and that kind of development puts pressures on our natural environment. And so this figure on the right here is looking at that expansion of urban area conversion from either farmland, ag land, or forest land. So 1980 to 1990, Atlanta was in the urban area of had about 25% growth in this time. So we're looking at this ever expanding growth that's occurring in land development in Atlanta. 1990 to 1996, it had a 47% increase in that growth. And then 2000 to 2010, a 35% increase. And again, you can imagine the last 10 years, it's continued to increase. So urban and suburban areas present a lot of environmental and social challenges, and several of you are probably very familiar with many of these. So one of these challenges is temperature modification. So urban and suburban areas have what's called an urban heat island effect. And that is typically that the temperature increases as the amount of hardscapes and like impermeable surfaces, concrete surfaces, glass reflecting heat, things that radiate and also absorb heat are in higher quantities in urban and suburban areas, so it increases the temperature of those areas as compared to rural areas or natural forest land. Urban areas and suburban areas also have a lot of water pollution. We have a lot of runoff with sediments. We have oil coming off of cars, lawn chemicals, fertilizers that run into our water, into our streams, and can pollute our water system. We also have a lot of noise, which can cause stress. Noise from roads, just noise from a lot of people living in a very close proximity to one another. We have a lot of air pollution, ground level ozone, carbon dioxide pollution from cars, volatile organic compounds. And in climate change, in our urban and suburban areas, they have less of an ability to respond to the effects of climate change, be that through a drought or heavy rains. It's setting up systems to respond to those kind of extreme weather events that might occur in climate change. Urban and suburban areas can be challenged by those. We have wildlife conflicts in urban and suburban areas, and I'm not just referring to nuisance wildlife. It's also making room for wildlife and giving them space to live as well. And a lot of the point of this webinar, we're going to be talking about soil, but in urban areas, we have a lot of soil disturbance. We have a lot of soil pollution and also compaction, runoff, erosion. So we've just talked about the environmental stressors and challenges in urban and suburban areas, but we also have these stresses on ourselves and our own health and well-being, our stress levels. And urban and suburban areas can provide challenges to social justice and equity. And oftentimes there's a fair amount of crime that can exist when people are living in such close proximity and various economic levels. Lastly, we have reduced green space because we have more condensed housing, more infrastructure going in, and so there's less places to have parks or for areas for wildlife to thrive unless we build those into our environments. So just looking specifically at some differences between the built and the natural environment, and this is really important as we talk more about soil and looking at natural soil systems and urban and suburban areas and looking at the soil surrounding our community trees. So looking at some differences here. So urban and suburban areas typically are less ecologically diverse and abundant. And this is important because in natural systems, we have this diversity of flora and fauna that can respond to different challenges that face a natural system. But when we have a less diverse flora and fauna and other types of systems that are in our built environment, in our urban and suburban areas, it can be more difficult to respond to challenges presented, for example, by climate change. Also in our built environment, we have greater pollution streams, be that water, soil, or air pollution, that natural systems may be able to mitigate better because of different ecological services that are provided by natural systems. And we also have altered ecological processes in our built environment. And we just mentioned some of these, but this can just be how decomposition works in a built environment versus a natural environment, how our water systems are set up in a natural environment versus a built environment. And so a lot of these cycles are interrupted in our built environments. These cycles that can help our environment sort of rise above some of the challenges that it would be faced with, like climate change. Okay, and then we've just talked about climate change here, is that generally these built environments are less resilient when faced with climate change. So let's talk about some things that can help ameliorate these challenges that we just discussed. Well, there's several things. There's a lot of different opportunities that our urban suburban areas have to address the challenges that they're faced with. But one of the best ways to address those challenges is through plants, specifically through trees. And so planting trees in our urban suburban areas can address a lot of these challenges we just discussed. And so what are trees most reliant on for their health? Soil. So one of the most important factors for soil or trees is the health of the soil. And so that is the basis of this presentation, and we're going to discuss some aspects of it. Some of you may already be soil lovers. Some of you may not, and not be that familiar with soil. Maybe you're still calling it dirt, but it is soil, and it has a number of benefits. And these benefits are not just ecosystem services provided to trees, but they're provided to our earth in general. So soil is the garbage disposal of our environment. It is the principal system that helps decompose different substances that are added to that, and so helps break down different organic matter that's applied to it, even helps break down pollution that's added to it. So it is the primary driver of decomposition is our soil. Soil also provides nutrients to plants, and those nutrients are funneled up the food chain to ourselves and other animals and plants. Soil also modulates temperature. Soil also allows for the exchange of atmospheric gases and soil gases, so oxygen coming in, carbon dioxide coming out of the soil. Soil also provides a lot of habitat for soil biota, and those are the drivers often of our decomposition process. So it's important that soil provides that habitat. Soil also provides a lot of structure. We build our built environment on, and plants live their life cycles out through. And then, of course, soil absorbs, stores, and releases water. And soil is one of the greatest stores of carbon. Okay, so let's think about how soil benefits trees specifically. And we're also going to talk about the vice versa of this, because it's a process here. This is a cycle. And so soil primarily benefits trees through giving them, one thing I don't have on here is room to grow. But soil also provides nutrients to trees. It provides different gases to trees, specifically oxygen. It provides place for support of trees, areas for trees to grow. And so that's room to grow, but also just the type of substance to grow in to support itself so it can grow upright. And then soil provides water for trees as well. Okay, so first we will discuss how soil provides support for trees and a place for them to root. But let's start first with tree biology here. We have the three different types of roots in a tree. We have the root plate, which I have an arrow here, and this is the connection between the stem and the roots, and this tends to be rigid. So the stem will be moving, and this area is sort of rigidly staying somewhat in place. It's sort of rocking back and forth. And then we have the structural roots that extend out from this, and this provides the support for the tree. These are roots that are a little bit larger. And then 90% of the roots are the fine roots, and these are very small fibrous roots that are principally responsible for nutrient and water uptake. So one thing I want you to notice in this figure is that a lot of people don't realize this is about what a root system will look like ideally. Many people aren't aware that roots can be 2 to 3 times or more wider than the canopy diameter. And they're usually only extending about 12 inches deep. That varies depending on the soil type. So this is really important to think about when we think about how trees are growing in urban and suburban environments. Okay, so I put this image here because I really like to think about the mechanical function of tree roots and wind, specifically structural roots. And I think of it like a tug-of-war contest. As the tree moves, the ropes or the roots are pulled and anchored to keep the tree upright. And then soil provides some of the strength and structure for this process to occur, so providing a foundation for the tree to anchor in. So imagine if suddenly 4 people on the side of this rope were removed from this contest. And this is exactly what can happen in urban areas, as you see in several of these images. So roots are damaged or given an insufficient area to grow. So look at some of the images on this slide. Okay, so we have this tree here. This is an oak. Clearly not given a lot of space to grow. I don't know how old this tree is, but I know that there's some others out here that were given a little bit more room, and some that have some shared root space that are the same age that are 5 or 6 times the size of this. Also, you know, we'll have construction damage here. Here was a new sidewalk put in, and instead of trying to work with this tree, they just cut off this root flare. And then we have a tree here that's sort of bulging out of its planter. This is another oak, and this tree clearly, to get to its mature size, is not given enough room to grow. And then we have a tree here. There was a barrier here, and the construction company wanted to lower the grade of this road, so they just cut through all of these roots and lowered the grade. And unfortunately, this tree started to lean a few days after they cut the roots, and they ended up having to cut the tree down, in addition to all of this damage to the root flare and some of the structural roots here. So this is not a good scenario, but this is a common scenario for a lot of community trees. So now let's examine other ecological services soils provide to trees. So we'll now discuss how soil supports tree growth. So a healthy urban soil needs to be able to infiltrate, retain, and release water, transfer gases like oxygen coming into the soil, CO2 going out of the soil, so tree roots can breathe. Also, a healthy urban soil needs to provide accessibility for root penetration. So in this slide, we're looking at what a healthy soil looks like. So this is sort of an ideal soil. An ideal soil is about 45% solid, so that's clay, sand, or silt, 25% air, and 25% water. Now this is going to fluctuate, this pore space. So these are pore spaces to either hold air or water. These will fluctuate, depending on if this has been after a rainstorm, how long after a rainstorm has the water drained out. And then this ideal soil is also going to have about 5% organic matter, which is seen here in the black area. So ideal soil is also going to have various pore size. So it's going to have large pores, so air can move in and water can drain out. It'll have small pores that can retain water to supply plant growth. It'll have this organic matter, which is where a lot of the nutrients and the soil food web, so the different microorganisms and macroinvertebrates will live. And then it has a range of particle sizes that are bound together to form aggregates. And this provides some of the structure of the soil that roots are really dependent on. So root growth occurs through two primary ways. So roots grow through pores larger than the root tip diameters. Roots also grow by enlarging small pores through pressure that they exert through turgor pressure. So they're expanding out and putting pressure on the soil. So in this figure, we are examining the ability of roots to grow in soil based on soil strength, and two plants are going to be examined here. We're looking at cotton and pine. So on the y-axis, we have root penetration. So that's the ability for the roots to penetrate into the soil. And we're looking again specifically through pine or cotton. And then on the x-axis, we're looking at two different types of pressure here in PSI, pounds per square inch, and then megapascals. And so we see as the strength of the soil is going up, meaning it's harder to press into, we see that the growth of the roots goes down, and at 2 megapascals or about 300 psi or 290 psi, that we see that root growth stops. It can no longer grow into this soil because the strength is too high. And so soil strength really increases when soil is dry, but it also increases when soil is compacted. Okay, so now we're talking about gas exchange. So tree roots need oxygen, as do microbes, and they both need the soil to release carbon dioxide. So we have a couple of figures here, oxygen coming in, carbon dioxide going out. So in this figure, we're examining the ability of oxygen to enter the soil based on how much water is in the soil. So let me explain this figure here. So on the y-axis here, we have oxygen diffusion. So this is oxygen coming into the soil. And then on the x-axis, we're looking at air-filled pore space. So soil has pores, as we talked about earlier, and it either can be filled with water or air. So down here on the left side of this axis, we're looking at a saturated soil. So soil that has just received a heavy rainfall, it's full of water and has less air. So that means oxygen is not able to enter into the soil. On this side, we have a very dry soil, and so oxygen is able to enter, carbon dioxide is able to leave. And what this figure is showing is that the soil dries out, it's easier for oxygen to diffuse into the soil. And so what this figure is basically touching upon is that saturated soils limit gas exchange, and they limit root growth and health as a result, because there is limited gas exchange. Okay, so let's now discuss soil compaction, which is great for construction, but not great for plants and soil. So soil compaction is the compression of a soil resulting in a reduction of the overall pore volume. And you can see that in this image here. So the soil is being compacted. So remember that pores facilitate water and gas movement and root growth. So soils are compacted at the surface from foot traffic, and they're also compacted at depth from heavy equipment. So an undisturbed soil, we talked about sort of that combination of different things, the soil solids, the air, water, and the organic matter. And then in a compacted soil, we have a lot more of the solid. We have about a 12% air in the pore spaces, or overall about 24% pore space. So we want about 50% pore space in an ideal soil. But as you see, this pore space is reduced. So that means that there's less room for water to go through, or water gets trapped, and there's less room for oxygen to diffuse into the soil and carbon dioxide to release. And also, we see that there's a lower percentage of organic matter often in a compacted soil. In a compacted soil, the bulk density goes up. So I'm just going to review what bulk density is. So it's the weight of soil in a given volume. Bulk density increases with compaction and tends to increase with depth. And bulk density varies depending on the soil texture. So you really need to keep that in mind when you get a value for bulk density. You really need to know what the soil texture is to determine if that's a compacted soil. Bulk density generally is used to indicate the degree of compaction based on soil texture. So when you have a compacted soil, there's going to be greater resistance to root growth, meaning roots will have a harder time growing. There'll be less pore space and less water infiltration. This figure examines an example of compaction, and we're looking at two different soils. One is a natural undisturbed soil in green, and then we're also looking at a compacted construction soil in pink. Note that the construction soil has both surface and deep compaction. I also want you to note this orange line here. This is a line down the middle noting where the growth of roots is limited. So this is where roots are really having a hard time growing into the soil. So I put this image of a soil profile on the side here because what we're looking at here, this is the soil surface at 0, and then we're going down into the soil here. So we're measuring at depth. This is in centimeters. For those who are not metric literate, I've put some inches here just to give you a reference point, so about 12 inches. And so again, we're looking at this resistance to penetration. We see that this native soil has pretty good low resistance to penetration, especially at the surface. As we move down, it increases a little bit, but this is actually pretty good. Like roots will have a much easier time growing into this soil. But when you have this soil that has been compacted, and this is primarily from foot traffic and heavy equipment at a construction site, we see that this is outside of the limit of how roots can grow healthily in trees or other types of plants. But oftentimes when you see a post-construction site, when they're going back in to put in plants, it's hard to determine that they're actually ameliorating all of this compaction. And you see that years later in the tree health and growth that's occurring on these sites. Okay, so these images show a typical construction site and the compaction that can occur, the heavy equipment that's on the site, and oftentimes we're having a house built and then we're having plants being put in right afterwards, especially trees. Here's some of the construction around homes and businesses, and I wanted to put an image in here of foot traffic, and this can be root limiting. This pathway, as you can see, there's nothing growing on it. Urban areas, often through compaction or crusting, can have very poor water drainage, and this greatly impacts soil function and tree health and mortality. So this is a really common site. We have these islands that are built into parking lots, and they're like a bathtub. Oftentimes the trees are planted up in a mound on this, but unless it's built in, there is not a good way for these areas to drain. And so they can fill up with water, and then that water is slowly either evaporated or transpired through the tree. But as you can imagine, this puts a lot of stress on the tree, and a lot of stress on what type of soil is in this. It's saturated and then it dries out. So it's a common like wet, dry scenario. And then you have these areas like this image up on the top right, where you have this tree that's sitting in its own water and it's not able to drain out. And so this, again, provides this difficult oxygen diffusion scenario for the tree. So in this next section, we're interested in examining chemical and biological aspects of a healthy soil and how these support tree growth. Okay, so a healthy urban soil needs to be able to adsorb and release essential nutrients. A healthy urban soil needs to mineralize nutrients from organic matter and have an absence of contaminants, support soil animals and microbiota, who are, again, principally responsible for that decomposition process. And then a healthy urban soil, in any soil, should support mycorrhizal growth. So this figure examines a soil particle surrounded by soil water in blue, which is likely part of a soil pore. So those pores are what are holding the water in the oxygen or the gases. And we're also seeing a tree root growing into this pore where the soil water is. So this figure demonstrates how soil particles and coatings like clay, so the particle and the coating, and iron oxide coatings, and also organic matter hold on to or adsorb and also release nutrients into the soil water, where they're then taken up by plants through the roots. So as you can see, the soil particle and soil water contain essential plant nutrients like potassium, or K, as you see on here, calcium, or Ca, and this is sort of an ideal scenario in a soil. We have good exchange, we have a good availability of these nutrients being held onto these particles, so retained in the soil, the soil is able to hold on to nutrients, but then it's also able to exchange them with the soil water for plant uptake. So I just wanted to demonstrate this figure just so you see how nutrients are provided and held in the soil. So the availability of nutrients in a large part is influenced by the pH of the soil, where nutrients are more or less available based on this pH. So a slightly acid pH increases nutrient availability, and we see that here. So this is the best overall availability of all of these essential plant nutrients, and this is generally between 6 and 7, the pH scale. So, however, urban soils present different challenges. So urban soils trend towards more basic or alkaline soils because they have a lot of wastes that are added to them and pollution, like construction debris. That could be drywall or concrete, boron, petroleum, fertilizers, all are influencing the pH of the soil. And this leads to some nutrient deficiencies or toxicities. And iron is one common plant nutrient deficiency seen in urban soils. I don't know if several of you have seen this, but I have seen this commonly in urban areas. This is iron chlorosis. So this actually isn't a true deficiency. This is sort of a pseudo deficiency due to pH. And so a remedy to this is lowering the pH of the soil so iron becomes available to the plants again. So soil pH is really essential in the functioning of the soil, but also for the health of the trees in accessing the nutrients that they need. Okay, so this slide is just showing some common scenarios in an urban and suburban area. You have this construction waste. Next to this house is some concrete residue that can come into the soil, affect the pH, raise the pH, cause some of the problems that we saw with iron chlorosis. We have waste that occurs around our trees. So this could be in the form of urea, just excessive nitrogen coming into the soil in some urban trees. Also, we're looking at just these spaces, having this room to grow and having room to access the nutrients that it needs. So where in this image do you see a natural source of nutrients? There's a grate over this tree, so the leaves falling are going to have a hard time getting in here and breaking down. I mean, unless they're fertilizing this tree every now and then, this is very difficult for this tree to gain what it needs in the way of nutrients. So I put up a slide here of structural soil. Structural soil in a lot of ways has been a solution to meet the needs of hardscapes and having a soil that can take the type of compaction that's needed for these structural hardscapes, but also be able to plant trees in. But one of the great challenges about structural soil is that it has such a low amount of nutrient absorbing capabilities, and so a way for the trees to get nutrients over the long haul is an issue with structural soils and why they're a challenge for longevity of trees. Okay, so this slide we're looking at what soil biology brings to the health of trees and also the health of soils. Soil biota play an essential role in the soil and really for the health of all plants. Again, I talked about they are essential in that decomposition process. But soil biota, and this isn't, I'm not just talking about soil, bacteria or fungus. I'm talking about also the creatures, the micro and macro invertebrates that live in the soil. They help create pores. And these pores help create this low resistance to root growth. Sometimes they can emit substances that help with the binding of soil particles. They can lower bulk density overall by creating this pore space. And this pore space leads to better drainage. Soil biota, though, in order to thrive, they need moisture. And this is generally at field capacity. So after a storm, after the gravitational water is sort of drained out of the soil, they need moisture to carry out their activities. And that's important for the mineralization. So mineralization is taking the organic matter it's not plant available yet, and they convert it into a plant available form and breaking down into basic nutrients that then go into the soil water where roots can take those nutrients up, or if they absorb to the soil particles where they're stored and then later released into the soil water. So we need moisture to carry out that process. Also, we need a slightly acidic pH for a high diversity of soil biota to carry out the plethora of decomposition processes and other benefits that they provide to soil. So we need a couple of things for the soil biota to really thrive. Okay, so let's talk about mycorrhiza now. So mycorrhiza play a vital role in soil with trees and other plants. Mycorrhiza have a symbiotic relationship between roots, and it is a symbiotic relationship between the roots and the fungi. One thing to keep in mind is that the mycorrhizae are obligate aerobes, meaning they require oxygen to carry out their basic functions. So they do not form well in saturated soils, and that's going to occur when you get these compacted soils that don't drain well. Okay, but let's look at some benefits. This is why we want to create healthy soil. They help increase nutrient uptake, especially phosphorus. And these nutrients are supplied to the trees in addition to the mycorrhiza. So they also increase root longevity. They help protect the trees against disease. They increase contaminant tolerance that trees have to face. They increase heat tolerance of trees. So in drought scenarios, the mycorrhiza can provide some relief in that regard. And then they can increase the pH extreme tolerances of the trees and other plants. Again, they need oxygen, though, to thrive. We talked about some temperature modulation earlier that soil can affect. And again, these are obviously is not typical of our southern environment, but this image is probably fairly common. We're looking at a more desert area here, but this is just an example as we're looking at temperature. Temperature is measured in this scale here. So the blue areas are cooler. You move up to the red areas, they're a lot hotter. And on this image to the left here, thermal image, we're looking at an increase of up to 131 degrees Fahrenheit, and the image to the right goes up to 137 degrees Fahrenheit in these red areas. So everything that's red and orange and yellow are hot. Red is the hottest. And so you're comparing where these plants are growing compared to where these hardscapes and these impermeable surfaces that are radiating, storing and radiating back a lot of heat. And you think about the stress that occurs around these plants that are exposed to this heat. And we think about these areas that, like this tree out here is almost entirely blue out here, and how this area protects the tree because it's modulating the temperature in this large soil area. I know that there's other things here. There's plants that are involved in modulating the temperature, but also this image is just to get you to think about the amount of stress that the heat can put on trees and how soil can help protect that, and how soil moisture can help protect that. But we also have to protect the soil to protect the trees. Several of you may know that 140 degrees Fahrenheit is the known lethal temperature of plant tissues, but cells and tissues will die at lower temps if they're exposed to them for long enough. And so that can occur in these scenarios here. So here's just an example of that. That's very common, something you could see in Georgia or some of the states that you're living in. You know, we've got a dark colored mulch here. We have a very small planting area, and we have asphalt, which retains and radiates back a lot of heat. So these trees are going to face a lot of stress as they're continuing to grow. All right, so I just wanted to shift gears here, and we're looking at some pretty ideal scenarios for trees in urban and suburban areas. We're looking at shared root space. We're looking at a closed canopy. We're looking at ability to access a wide variety of nutrients. Even if there's a little bit of compaction out in these areas from people walking, there's a greater area for the trees to mine for nutrients and to grow. These are some ideal scenarios, but this is not often what we're seeing. We're often seeing scenarios more like this, where we have small planting holes. We have small areas in parking lots where trees are given really sort of a cap on their life because of the small area. And so we have to think about these areas and potentially think about trying to provide more soil space for these trees to grow in so they can survive in these very challenged conditions. So again, we're going back. Community trees need healthy soil. They need nutrients, they need room to grow, they need oxygen, they need support, they need areas for growth and the type of good soil to grow in, and they need water. So how do we have healthy urban soil? So I wanted to go through a few different ways that we can create healthy soil. Okay, so we need to protect soil and trees during construction, but I want to really emphasize protecting the soil here. This isn't just about protecting the tree roots. We want to get in and we want to protect the soil because it's costly and it's time consuming to ameliorate damaged soil after the fact. So protecting it in the first place, if at all possible, is best. So since some of the worst damage to trees occurs to the roots, this usually means it's occurring to the soil. So this is where some of the most damage occurs during construction. All right, so some recommendations, and this is similar to tree protection areas, but we're really thinking about the soil here, is creating exclusion areas to protect the soil. And this, ideally would be extended outside of the critical root zone if possible. We want, again, we remember what the root system looks like in a healthy tree. It expands out 2 to 3 times the diameter of the canopy, and we want to try to protect as much of that area as possible for our trees, and so soils can carry out their basic functions. So we can designate and define entry and exit ways for heavy equipment and supplies. So having those pathways coming in and out that would be commonly traveled paths and really discourage traffic outside of those. Also consulting an arborist and having an arborist work with the contractor and putting in tree and soil recommendations in the construction plans and specifications. And then also mulching areas to protect the soil and the roots of the trees. So we have a tree exclusion zone here, but this is also an image showing, they've sort of, I don't even think they've come out to the critical root zone here, but as you can see, they've pretty much compacted and altered all the soil around it. And so this is a fairly large tree. They didn't even come out to the drip line of this tree to protect the soil. And so, this is going to take a lot to ameliorate these conditions around this tree. Okay, so this is just an image looking at the critical root zone. And for 1 dBH, it's saying you want to come out about 1.5 foot of the radius. So this is recommended to protect this area during construction. Again, I know that some lot sizes are limited, but if we could come out and protect the actual root zone of this tree and protect more area, this would be more beneficial to the tree in the long run and the health of the tree if the objective is to save that tree. Okay, so we can correct soil compaction, and we should correct soil compaction following construction or just long-term use of people walking over a site, or maybe someone's been parking, under their trees or on their lawns. There are ways to address surface compaction and deep compaction. Rototilling is one way to address surface compaction. You can create what's called a hard pan, though, about 8 inches deep, and so that would have to be broken through eventually. Air spading is a great way to break up compaction around trees and to encourage new root growth. And so this is air spading going around this tree. It looks like it was planted a little bit deeply here, but this will help create new fine roots, better soil mining for nutrients and water uptake. Vertical mulching is another way to break up compaction. And this is an example of this. It looks like they've used an air spade, so you drill holes down about 8 to 12 inches. And sometimes people fill them with compost, but it could also be a blend of the native soil or topsoil and a mixture of compost. This is another way to bring in more organic matter in a different type of soil to help loosen up the compaction around this tree. So we also have something called radial trenching, which I don't have an image of, but it's digging out trenches radially around the tree, and then you can backfill those trenches with a mixture of topsoil or native soil amended with finished compost. There's also something called air fracturing. I'm not as familiar with that. I'm more an advocate of these types of techniques, especially air spading. So I didn't include that one on here, but I would say one of the greatest ways to ameliorate compaction, though it will take a long time, is mulching. Good hardwood mulch, whether that be bark mulch or wood mulch, it's just going to take a much longer time to carry that function out. So if you're okay with waiting and your trees don't seem heavily stressed, then that could be an alternative to these other methods. So deep compaction is usually going to be broken up with a subsoiler. If anyone's seen one of those, it's a fairly large equipment. Sometimes they're called rippers. They break down, go down into the soil, 2 or even 3 feet and break up the hard pans and the soil compactions. There's another technique I wanted to go over called scoop and drop, or Virginia Tech came up with soil profile rebuilding. And this is a method to address deep compaction and surface compaction over a large area. Okay, so at the end of the presentation, I have a link to more details about this, I'm just very briefly going to go through the scoop and drop or soil profile rebuilding method. But this is a great method for planting trees, and this is compared to using like a tree spade. And so you're breaking up a larger area, so you're giving a larger, less compacted area for tree roots to grow into. Okay, so the steps are that you add 4 inches of finished compost over sort of this compacted soil area, and then you subsoil the soil with a backhoe to a 2-foot depth over a large area, and you're usually starting at the front and moving back. So you don't want to drive over what you've already loosened up. And the idea is that you scoop down 2 feet with the soil, existing soil, and the compost, and then you drop it. And then after you've loosened up this soil, you're going to add 3 to 4 or up to 8 inches, depending on how much topsoil was removed, of topsoil over this area that you've just scooped and dropped. And then you rototill to a depth of about 6 to 8 inches, just that surface soil, because you want to combine that topsoil with the existing soil and the compost so to have more of a homogeneous layer there. And then you allow this to settle so it's ready to plant trees in. Okay, so the next thing is that we want to provide adequate soil volume. So tree roots need room to grow to maturity, but oftentimes they are planted either too close together or given an insufficient volume of soil to grow in. So this leads to trees competing for water and nutrients, which stresses trees during a drought and can even lead to mortality. So insufficient soil volume also can lead to gaps in the canopy, where a closed canopy may be desired. So this example only includes sort of the top 3 feet of soil, and this was a figure that was created by Jim Urban in 1992, so I definitely want to give credit to him for this. Provided a link to this document at the end of the presentation so you can access that. So he just provided an example here. So this is basically saying this is in an urban area, so this is to think about what kind of soil volume you need to grow a tree to maturity. So if you're trying to get a 16-inch diameter tree with an 800 square foot crown spread, then you want to have 1,000 cubic feet of soil volume down to a 3-foot depth. And so that can be utilized in different specifications, whether that be a landscape architect drawing or a rendering for a site, and putting in those specifications, because oftentimes trees are not given enough soil volume to grow in, and this is a really good recommendation to follow. Also, it's great to provide shared root space, so trees can help hold one another up. They can exchange nutrients through mycorrhizae. Providing this shared root space and providing more room for the tree roots to grow is advantageous in any scenario. We saw some pictures of that earlier. Really maximizing a vault size of a tree in an urban area, even in a suburban area, and combining it with porous pavement and other means to extend the volume that trees have to grow in is really important. So this is a silvocell. Some of you may be familiar with these. This provides structural support for the hardscapes over the trees, but enables trees to grow underneath, can provide some aeration and some water drainage as well under these areas. And we see that these tree roots, instead of being limited due to compaction under these hardscapes, they can now grow out and realize this larger canopy spread and greater root volume can be obtained. All right, so this is using some impermeable pavement. This is not ideal for all scenarios, but this was a picture from Seattle. And because they kept having people walk over these areas, this was a solution of theirs that has enabled these trees to have a greater longevity. And so this has really worked for that city and could be applicable to other dense urban areas as well. And then we have another image here of the shared root space. So this is, again, we could always give these trees more room, but instead of just having this much room for them and concrete, this enables them to grow roots out in a wider area, and maybe even if they can grow under this concrete, access this area over here as well. Okay, so we also want to protect the soil surface by either installing barriers, as you see in this image on the left, so people aren't walking over this. This is just tall enough so they don't really want to lift their knee over it. So this was a well-placed barrier so people wouldn't walk in here, disturb the soil and compact it, or add contaminants to it, but also adding a nice layer of mulch. I mean, as opposed to this being bare soil, this helps the soil, which then protects the tree roots. Okay, so improving soil drainage. So there's different drainage systems. We saw some impermeable pavement and tile options here. We see some areas that can collect rainwater and funnel them away. There's some trees planted in this image down here. We have some filter strips and trenches. We can, there can be designed in a wetland or a pond to channel off water, because, stormwater is an issue and trees can help ameliorate that, but we have to help trees and not having them being flooded with water in urban and suburban areas. They need water, and they can help transpire that water and uptake that water and even slow the impact of that water down, but we need to help them in giving them areas where water can then also drain away and allow oxygen diffusion to occur, allow soil microbes to thrive, and allow for root growth to be optimal. And then we want to also maintain a balanced soil chemistry. So protecting the soil from contaminants. We've already seen these images. So just ensuring that, working with contractors, working with homeowners and educating them about how to protect the soil, because, you put this down, maybe it's applied somewhere and people forget about it, but it has entered the soil and it has impacted the soil. So if a tree is planted here, there are going to be repercussions. And so taking a soil test, looking at a foliage test to determine what is existing on site and ameliorating it with either pH adjustments, fertilizer, if needed. Most importantly, using pesticides, fertilizers wisely, avoiding contaminants on soils that can impact trees. And lastly, we want to try to mimic natural soils as much as possible and really supporting the soil biota, because again, these are the workhorses that are helping decompose matter, making it available to trees and other plants that funnel up the food chain and influence our lives on a daily basis. Okay, so this is all that I had. I know that I glossed over a few areas because we have an hour, so there's not a lot of room to go into a lot of depth. And I wanted to focus primarily on just trying to emphasize that soil is really important to our ecosystems, and the health of the soil and the quality of the soil is really important. As well, it is important to support our community trees that provide a number of benefits to us in our everyday lives and improve the environmental, social, economic quality of life and health of life in urban and suburban areas. There are some resources here, so definitely check these out. And I will have this presentation. It's recorded right now. I'm going to upload it to the webinar portal where you saw this, where you came to this webinar to log on, and you'll be able to watch this again so you can access some of these resources. We also have another webinar coming up on June 11th. I believe Jason will be doing this webinar. It's called Tips for Choosing the Right Yard Tree. So be sure to check that out. Also available for ISA CEUs. And if you have any questions, please feel free to contact myself or Jason. And also wanted to provide a special thanks to Dr. Morris for his contribution to this webinar.